Bismillahirrahmanirrahim. Assalamu alaikum. I am Muhammad Ans Khalid, your course instructor of data structure and algorithm. In the previous lecture, we discussed introduction to data structure, types of data structure, algorithm complexity, big notations, and recursion. Today we are going to discuss about array searching like linear search and binary search. First of all, we understand the concept of linear search. Linear search is a method of finding a target value within an array. It sequentially checks each element of array for the target value until the match is found or until all elements have been searched. Linear search checks each element one by one until it finds the target or reach the end. It does not need the data to be sorted, which makes it simple but not very efficient. Now let's look at the simple real life example of linear search. In a telephone directory sorted by name, if we search using a phone number, we must check each entry manually. That is a linear search. Here are the key benefits of linear search. The best thing about linear search, it is simple. We can use it on any array, sorted or unsorted. No special requirements. It is simple and easy to understand and implement. It does not require the data in array to be sorted in any particular order. Along with the advantage, linear search also has some limitations. It has poor efficiency because it takes a lot of comparison to find a particular record in a big files. The performance of algorithm scales linearly with the size of input. Linear search is slower than other searching algorithms. Let's visualize how linear search works step by step. Here is the array of 9 elements, and we want to find the value minus 86. Linear search always begins from the first element and check each value one by one until the target is found. So let's go step by step. The first step is look at index 0. Value is minus 23. It does not match minus 86, so we move to the next element. The value is 97, still not equal to minus 86, so continue. Look at the index 2, value is 18, not a match, keep going. Look at the index 3, value is 21, again not equal to our target, move next. Look at the index 4, value is equal to 5, still not match, continue searching. Look at the index 5, value is minus 86. This time the value match our target. So we stop the search right here because we found the value minus 86. The algorithm returns the position of the value which is the index 5 in the array. If the value had not been found, the algorithm would continue checking until the last element and return them not found. Let's translate the linear search logic into a simple natural language and pseudocode. This describes the logical step of linear search. We initialize index to 0 and check each element until we either find the value or reach the end. The first step is set I to 0. The second step is if I greater than n, then go to step 7, which is print element not found. If a of I is equal to x, then go to step 6, which is element found at index I, and go to step 8. If not found, not equal to, if a of I is not equal to x, then set I is equal to I plus 1, go to step 2. Now let's analyze the performance of linear search in different cases. In the best case, the target is in the first element of the array, so the search takes some teeny and constant amount of time. In the worst case, the target value is in the last element of the array, so the search takes an amount of time proportional to the length of the array. In the average case, the target value is somewhere in the array, so on average the target will be the middle of the array, so the search takes an amount of proportional to half the length of the array. Now let's move to on the binary search. The binary search can be implemented only on sorted list of elements. The process starts with finding the element at the middle of the list and comparing the key value with the element in the middle of the list. If the value of the key is less than the element at the middle, then search process the key to the list up to the middle element, and if the value of key is greater than element at the middle, then the search the key from middle element to the end of the list. Binary search works only on sorted data. We repeatedly check the middle element of array and decide whether to go left or right based on comparisons. Here is the simple explanation of how binary search works. The initial search region is the whole array. Look at data value in the middle of the search region. If we have found your target, stop. If your target is less than the middle data value, the new search region is the lower half of the data. If your target is greater than the middle data value, the new search region is the higher half of the data. Continue from step 2. Now let's see the benefits of binary search. Binary search is much more efficient, fewer comparison, especially on large data. However, binary search has a required it. The array must be sorted. If data is not sorted, we cannot apply binary search without sorting first. As you see, we locate the middle, compare and eliminate half and data until we find the number. Now we will perform binary search on the sorted array. Here is the array of 9 elements. The first element is -86, the second element is -37, the third element is -23, the fourth one is 0, the fifth one is 5, the sixth one is 18, the seventh one is 21, the eighth one is 64, and the ninth one is 97. Our goal is to find the value 18. Binary search always start by checking the middle element and then reduce the search range. The initial step is the low is equal to 0 and the high is equal to 8 index. Now we find the middle element. 0 plus 8 divided by 2 is equal to 4. It means the fourth index number is the middle element, which is 5. Now, since 18 greater than 5, we ignore the left half and search in the right half. New range low is equal to 5 and high is equal to 8. Midpoint is equal to 5 plus 8 divided by 2 is equal to 6. The mid index is 6. Value at index 6 is equal to 21. Compare target 18 with middle value 21. Since 18 less than 21, we search in the left half of this range. Now low is equal to 5 and high is equal to 5. The mid is equal to 5 plus 5, 10 divided by 2 is equal to 5. Mid index is equal to 5. Value at index 5 is equal to 18. Compare target is equal to 18 with the middle value 18. Now the value found. So binary search return value 18 found at index 5. We locate 18 in just 3 comparison by cutting the search space in half each time. Binary search only works if the array is already sorted. It turns out the sorted in huge issue in computing and the subject of the next lecture. Let's break binary search into a easy natural step and pseudocode. We basically ignore the half of the element just after one comparison. Compare x with the middle element. If x match with middle element, we return the mid index. Else, if x is greater than the mid element, then x can only lie in right half subarray after the mid element. So else recursive for the left half. Here is the pseudocode of the binary search. A is equal to sorted array, n is equal to size of the array, x is equal to value to be a search. Set lower bound is equal to 1, set upper bound is equal to 1. While x not found, if upper bound less than lower bound, exit x does not exist. Set midpoint upper bound plus lower bound. If array of midpoint less than x, set lower bound is equal to mid plus 1. If a of midpoint greater than x, set upper bound is equal to mid minus 1. If a of midpoint is equal to x, exit x found at location midpoint and while end procedure. Time complexity of binary search. Think about how it operates after you examine a value. You cut the search region in half. So the first iteration of loop you search region is the whole array. The second iteration it's half the array. The third iteration is the quarter of the array. The kth iteration is 1 by 2 k minus 1. Finally, let's discuss why binary search is faster using its time to complexity. Binary search cuts the each that binary search cuts the data in half each time from n to n by 2, n by 4, n by 8. So its time complexity is big of log n.